So thank you very much and welcome to this presentation on distributional trees and forests. So this is joint work with Thorsten Hothorn and Achim Seileis, who are my supervisors and also the authors of the Party Kit package, and with Heidi Seibold. And all the material that I'm going to present to you here today is available on RForge, so that also includes the implementation, so you're more than welcome to try it out. Now let's start by looking at some of the tools that have already been developed in the field of regression analysis. So among the first were linear models, which were then extended to generalized linear models. Then, to also allow for nonlinear effects, generalized additive models were introduced, with the corresponding implementations being provided in packages such as MGCV, VGEM, or others. But until that point, only the mean of the response variable was modeled. But then generalized additive models for location, scale, and shape made it possible to model each parameter of a distribution separately. And so in that way, it was now possible to specify a whole distribution. And all these models work very well as long as we only have additive effects. But a different model that can also deal with non-additive effects are regression trees, which work based on the idea of separating the data into more homogeneous subgroups based on partitioning variables. But one problem that might appear here, as we can see in the right step there, is that trees impose these abrupt changes, these steps on the model, even in situations where there might actually be rather a smooth transition. And so one idea how to tackle this problem is to not just look at one tree, but to combine an ensemble of trees. And that's what's done in random forests. And here we can see on the right side that we do get this smoother effect here. And we also stabilize and regularize our model. And what we want to do now in distributional trees and forests is to combine all these ideas. So in particular, we want to embed this progress that has been made in the field of parametric modeling that we've seen before into the idea of trees and forests, and tree algorithms and forests. And we want to provide the corresponding implementation in a package called Distri, which is based on the package Party Kit. So our goals are to build a distributional model. We want to specify the complete probability distribution with all its features, so including location, scale, and shape. And by applying a tree algorithm, we're aiming at an automatic detection of steps and abrupt changes, and we want to capture nonlinear and non-additive effects and interactions. And by building forests, we're hoping for smoother effects and for stabilization and regularization of our model. So how do we build such a distributional tree and then also a distributional forest? Well, first of all, we have to specify a distribution. And here we do that by specifying a log likelihood function L, which depends on a parameter theta, which can be multidimensional, and the response variable y. And then with this function, we can estimate theta hat using the maximum likelihood method. And once we have this estimate of theta hat and our log likelihood function, we can calculate so-called scores. So scores are the values of the derivative of the log likelihood function by the parameter theta, with the estimated parameter theta hat and the observed yi plugged in. And they give us, these values, they give us information about how well the model fits our data. And ideally, they should fluctuate randomly around 0, such as we know it, for example, from OLS residuals. But here we really have one value for each parameter and for each observation. And of course, we want to use this information now, how well the model fits our data. And we do this by testing for associations or instabilities of these scores and each partitioning variable xi. So we're trying to find out whether there's any connection between how well our model fits the data and our partitioning variables, our covariates xi. And then we choose the one partitioning variable where we find the strongest association or instability. And we split along this variable, and we choose the breakpoint which leads to the highest improvement in model fit, which in this case is the highest improvement in log likelihood. So now we have a splitting variable and a split point. We can split our data into subsets, and in each of the subsets, we repeat the steps 2 to 4 listed here, in the subgroups until we meet some kind of a stopping criterion. This might, for example, be a minimal number of observations in the node or a p-value for the statistical tests that we had in point 3. And now we have a distributional tree, and if we build an ensemble of these distributional trees, we get a distributional forest. And each of the trees in this forest is built on a slightly different data set, and this might either be a bootstrap or a subsample. And in order to reduce the correlation among the trees, we're applying random input variable sampling. As to predictions, we have two different strategies, so one for trees and one for forest. And let's say we have one new observation, then in a tree, we would simply select a subsample of our learning data, which ends up in the same terminal node as our new observation does. And then we estimate theta hat on this subsample. So for all the values that are in the same terminal node, we would get the same prediction. In a forest, we can use the whole learning data for the estimation of theta hat, but we include weights here. So for each learning observation, we calculate such a weight by counting the number of trees in the forest, in which it ends up in the same terminal node as our new observation does. So a learning observation that is similar to the new observation will have a higher weight and then also a higher influence in the estimation process later on. And so now we have a weight for each learning observation, and we can estimate theta hat on the whole learning data set, but on the weighted learning data set. And in that way, we get more of an individual prediction for each new observation because we have these individual weights. So that was the theory. Now let's take a look at some examples. First of all, here we generated a data set consisting of a response variable y and one covariate, so one partitioning variable. And the conditional distribution of y is a normal distribution with a location parameter mu and a scale parameter sigma, both depending on x. And in this case, depending on x means that the value of x decides in which terminal node the observation is in. And in each terminal node, we have a fixed set of distribution parameters for the conditional distribution of y. So here in this example, we have the first split at 0.4. And on the left side, you see, so on the left terminal node, we have a scale parameter of 1. And on the right side of this first split, so the two nodes on the right side, we have a scale parameter of 3. So in this first split, we have a change in the variance in the scale parameter. And then we have a second split at 0.8. And here you see on the two right nodes there, we have a change in the location parameter from mu equal to 12 to mu equal to 4. So this is how we generated the data set. And if we apply distributional tree now on this data set, we get the following results. And we see, first of all, we got that right basic structure. And also the split points that were detected here are really close to the ones that we set in the data generating process. So the first one was at 0.4, so we got really close one. The second one is even the exact one at 0.8. And also the estimated distribution parameters are really close to the ones that we have set in advance. So if we just switch back, these were the true ones. For example, in the first terminal, or in the terminal node number 2 here, on the left, we have 4 and 1, and the estimated ones are 4 and 0.99. So we're really close here to the true parameters. And also in the other two terminal nodes, we had 12 and 3 as true parameters and 4 and 3. So the model seems to fit the data quite well here. And also when we look at the box plots in the terminal nodes, we can see that these changes were clearly detected. So first, this change in the variance on the left side and the two on the right side, and then this second change in the second split, the change in the location from a high value of 12 to a lower of 4. And since we have specified a distributional model, we can also compare the density functions here, and that again shows us first this change or the split in the variance, and then the second split in the location parameter. And here we have the location or the distribution parameters for this example plotted along x. In the red line we see the location parameter mu, and the colored area represents the variance, so that's mu plus minus sigma. And this just illustrates again that we really have these abrupt changes. We really have these steps in this example. And so this really was a perfect example to apply a tree algorithm on. It was built for a tree, since we had this tree structure also in our data generated process. So now we want to look at a more general situation where those transitions are not that abrupt, but rather smooth, as we can see it here in this case. So here again, we have the true parameters plotted. And so we keep this change in the parameters, so in the location parameter, from a low value up to a higher and then back to a low value. And we also keep the change in the variance. So we start with the larger sigma and gets a bit smaller and then larger again, independently of mu. So we keep these changes, but in this case now we have smooth transitions. And if we apply a distributional tree here, then we see that the tree struggles a bit with these smooth transitions. So those steps are a bit too rough, especially here in those parts where we have those smooth transitions. And on the other side, if we take a look up here where we have this change from steep to flat, it does capture this change quite well. Quite on the contrary, gamma LSS, for example, models the smooth part very well. So it basically captures the exact true parameters. But then when we get to this change from steep to flat, it starts to struggle a bit. It goes up too far. And also down here in the flat areas, it does have its problems with these changes. The distributional forest models the smooth part better than the tree did, not as well as gamma LSS did though. And the changes up here from steep to flat are also captured better than gamma LSS did, but not exactly as well as the tree did, but it did get both effects here. And especially when we look at all three of them together, we can clearly see that there are those parts here, those smooth parts, where the tree has its problems. Then we have those changes from steep to flat where gamma LSS has a few difficulties, and the forest stays always somewhere in between. And again, we have specified a distributional model, so let's also take a look at the variance here. But it leads us to the same conclusions. Again, here we see, for example, here the green area where the steps of the tree are simply a bit too rough. And here this blue area where gamma LSS goes up a bit too far, where those changes from steep to flat are. And again, the forest is somewhere in between those two. But now, of course, this was just one example, one specific example, and we want to compare those three models and their performance over a larger number of data sets and also over different situations. So let's say we have an additional parameter, kappa, that regularizes the steepness of the transitions that we have here. So for low kappa, we would have really smooth, almost flat transitions. And then as kappa increases, we would get steeper transitions up to almost a step function that we have seen at the beginning. And if we apply those three methods on this scenario, we get these results here. We compare them here based on the log likelihood of a new data set. And here we can clearly see that in the situation of smooth transition, gamma LSS is definitely the best choice here, while the tree obviously really has its problems here. And this forest performs quite okay. But then as soon as these transitions get steeper and steeper, gamma LSS starts to struggle here, while at the same time the distributional tree improves and gets better and better and even gets slightly ahead at the end. But overall, the dist forest is the one that stays more or less on the same level over the varying kappa, so over the varying steepness of these transitions. So it seems to somehow combine the advantages of both of the other methods, because it can capture the abrupt changes, because it has that tree structure in it, but at the same time it can model the smooth effects in a reasonable way. So it seems to be quite of a good compromise here, and especially in situations where we don't know what kind of effect we might have here. It seems to be, a good compromise. And one thing I would like to mention here is that in all the examples that we have been looking at here, we've only had one covariate, only one partitioning variable, in order to make it possible to visualize the results in a two-dimensional plot. But so we did not even have any non-additive effects or interactions between covariates, but these would actually be the situations where the trees and the forests can play to their strength, where they are particularly advantageous, because they can capture these non-additive effects and these interactions, which other models, parametric models, cannot. So to sum this up, there are clearly situations where a parametric model such as gamma LSS is definitely the best choice, and other situations where a tree structure might be advantageous. But overall, the dist forest, or forest, and here the distributional forest, seems to be a good compromise and a recommendable option, especially when we don't know what kind of interactions we have, when we have more than one covariates and we don't know how they might interact and what kind of effects might be involved here. And as I said before, there is a package called disttree. It's available on RForge in the PartyKit project. And it consists of the three main functions that are listed here. So there's distFit, which does the distributional fit using maximum likelihood method. And there we specify the distribution family by handing over either a gamma LSS family object or a custom list, which includes the necessary information, such as the log likelihood function. And here we do not use any covariates, so the distribution is fit to the response variable only. Then this tree builds distributional trees using either the C-tree or the mob function as a tree algorithm. And both of these functions are available in the PartyKit package. And both of them apply distFit in each node to fit the distribution model, and in that way to also get the scores. And here the covariates are used as partitioning variables in the tree algorithm. And then the dist forest builds an ensemble of dist trees, so we get a distributional forest. And here again, the covariates are used as partitioning variables in the trees. Yeah, and to come to an end here, I have a list of references and further literature, and I'd really like to thank you for your attention. Thank you very much.